Welcome again. And now we will apply the forward biasing to this junction J1. So in order to apply the forward biasing, what is required? We will apply some. This is the N type. This is P type. So to make it forward bias, we will apply this kind of polarity. So now this is forward bias. So this is a PN junction. Now forget about this J2. Forget about this J2 is not in the picture right now, and we will discuss this J2 later. So right now, what is the thing? So this is a PN junction, just like this that we have discussed now. But there are three major things that we need to understand. The first thing is this. Let me clear this. So this PN junction is just like this one, but there are few extra things. And what are those extra things? Number one, emitter is heavily doped. This we know. And why this is, we will understand it here. Number two, base is lightly doped. And number three, base region is very thin. In practical, it is order of few microns, very few microns. And the width of emitter and base are in tens and hundreds of microns. So we know, you know that micron. So micron is the unit of distance, 10 raised to the power minus 6 meter. So this is very small. And I hope you have seen the transistor. And the transistor is a plastic coated. The protective coating is on the transistor, and there are 3 leads are coming out from this protective coating. And these 3 leads are coming. If this is a transistor, I hope you have seen the transistor. And these 3 leads are the connections from emitter, base, and collector. These 3 leads are the connections from the, and inside that protective coating there is a transistor. So you can understand that is very thin. Okay, so this is some practical information. Okay, so beside this PN junction, these 3 factors are extra for the transistor. We need to understand the 3 geometric and doping aspects of the transistor, and why we have made transistor like this. So we have done these things very deliberately with the transistor, and now we shall see the use of these 3 factors, or use of these 3 geometrical and doping aspects of the transistor. These are the 3 geometrical and the doping aspects of the transistors, and now we shall see the use of them. Okay, so here we know this is the famous. So here what we can understand, emitter is heavily doped. So what do we mean by emitter is heavily doped? Sorry. So the electrons, there are lots of free electrons. There are lots of free electrons are available in the transistor. Sorry, in the emitter region. And base is lightly doped. So holes are here. You can understand the meaning of lightly doped and heavily doped. I have already discussed the meaning of lightly and heavily doped. It means for every, if this is heavily doped, then we can say for every 10 raised to the power 3 atom, we are doping 1. And if this is very lightly doped, then for every 10 raised to the power 8 atom. So there is a definitely for the same reason. अगर हम बात करें heavy और light का मतलब अगर समझना चाहें, तो जितना रीजन ये बेस है उतना ही अगर हम यहाँ पे लें उतने बराबर का मान लीजिए, तो यहाँ पे नंबर ऑफ इलेक्ट्रॉन्स बहुत ज्यादा होंगे. नंबर ऑफ इलेक्ट्रॉन ज्यादा होंगे एज कंपेयर टू नंबर ऑफ होल्स इन द, यानी कि अगर हम ये दोनों बिल्कुल बराबर बराबर विड्थ के लिए जाएं, इफ वी टेक द इक्वल विड्थ ऑफ this base region and emitter region, then the concentration of electrons will be higher than the concentration of holes. So this is the meaning of heavy and lightly doped. And the third and the most important point is base region is very thin. So actually we can draw a large figure and more large figures in order to make you understand. I can draw larger of figures, but practically this is very small. Okay, so you need to understand this is practically well, so we are drawing this like this in order to make you understand, but practically this is very small. So now what we will discuss, if this is the n region, okay, so and we have applied this battery. So as soon as we will apply this battery, let us suppose this is a switch and we have closed this switch now. So if we close this switch now, so now this junction J1 is forward bias. What will happen? This barrier, this potential barrier which was initially here, we know that there will be some potential barrier or the built-in potential, and now we have applied a reverse electric field, uh, and that electric field is opposing that potential barrier. That barrier is broken now. So if that barrier is broken now, what you need to understand, these electrons will go there because the diffusion process, diffusion is a natural process, there is a concentration gradient, again all those things that we have already discussed in the p-n junction will happen. So these electrons will move here, and while moving they will recombine, definitely if they will go there. But the point is this, base region is lightly doped. So what we need to understand, if the 4 or 5 electrons are coming from here and this is very heavily doped, so there are only one or two hole for him. It means like if the population is very much high, यहाँ पे 10 गुने 100 गुने हैं, यहाँ पे 5 है, यहाँ पे 10 है, यहाँ पे 20 है, तो हर एक 5 पे एक आ रहा है. तो ये आपको ये just I'm just using the numericals, I'm just using the numbers in order to make you understand. Okay, तो यहाँ पे बहुत सारे इलेक्ट्रॉन है, यहाँ पे बहुत सारे, यहाँ पे होल्स हैं काफी सारे. बट एक चीज, जब यहाँ डिफ्यूजन प्रोसेस स्टार्ट हो जाएगा तो इलेक्ट्रॉन्स इधर मूव करेंगे. जब इलेक्ट्रॉन्स मूव करना शुरू करेंगे और होल्स भी इधर मूव करेंगे, डेफिनेटली होल्स भी इधर मूव करेंगे, बट इलेक्ट्रॉन्स हैवी, यानी यहाँ पे इलेक्ट्रॉन्स का नंबर है वो बहुत ज्यादा है. पहली चीज, पहला पॉइंट जो हमें समझना है. दूसरा पॉइंट, बेस इज वेरी लाइटली डोप्ड. बेस जो है वो लाइटली डोप्ड है, यानी कि यहाँ पे नंबर ऑफ इलेक्ट्रो होल्स की, नंबर ऑफ होल्स इज लेस, number of holes is less. And third thing is this base region is very thin. So this is the most important thing. What will happen here? The electron, but we know that for recombination, we know that for recombination, the electrons from the emitter side, which are coming from the emitter sides, require a certain time. Definitely here, if the electrons are moving here, but here the space is available, so electrons are moving here, this is equal, we have discussed. But here you can see these electrons are moving here and they require certain time, because यहाँ से move करेंगे और इलेक्ट्रॉन को कहीं होल मिलेगा, फिर वो प्रोसेस होगा रिकॉम्बिनेशन का, एनर्जी रिलीज होगी, तो वो जो भी प्रोसेस होगा उसमें कुछ certain finite time लगेगा. But what we are doing here, we are deliberately making this base region very thin. So what will happen? They will cross this base. In order to make the electrons coming from the emitter side to cross this base, we have make this base region very thin. Very thin. We have make this base region very thin. Now what is happening? These electrons, most of the electrons will cross the base region. Why? Base is lightly doped because जब यहाँ से 5 चल रहे हैं तो उनको एक ही मिल रहा है, और वो एक भी जितना टाइम, बिकॉज वो मूव कर रहे हैं। यहाँ पे आप देखिए, जब एक और चीज और आसानी से समझने की कोशिश करते हैं कि जब यहाँ पे डिस्टेंस कम है और ये एक पर्टिकुलर वेलोसिटी से आ रहे हैं, वी नो दैट थर्मल वेलोसिटी होती है, डिफ्यूजन प्रोसेस है तो इसमें ड्रिफ्ट वेलोसिटी का यूज ही नहीं है। सो बेसिकली द थर्मल वेलोसिटी से वो इलेक्ट्रॉन्स मूव कर रहे हैं। वी नो दैट देयर इज थर्मल वेलोसिटी, इनहेरेंट थर्मल वेलोसिटी ऑफ द इलेक्ट्रॉन्स, सो दे आर मूविंग, and this region is very thin, this distance is very thin, then definitely we know that if the velocity is very high, then the time taken to move this region will be less, because this distance is small. This distance is very, very small. We know that if this distance is very small, then definitely what will happen, the time taken to cross this distance will be small, because the velocity is not changed, velocity is high already, and we have provided the base region very thin. So what we need to understand here, most of the electrons will cross the base region. It's like 90, more than 98% of the electron, more than 98% of the electrons will cross the base region, and very less, like 2% of the electron will recombine. And if those electrons will recombine, then what will happen? This PN junction is here. So those electrons will make the base current. How? Again, you know that there is a recombination here. And again, the new holes will generated by the battery positive terminal, like here. And there will be a base current. Base current because of those electrons which are recombining. But the probability of recombination is very less probability. So here we talk about in the terms of probability, and it's like this: 98 to 99% of the electrons are going through the base region, and now they are reaching at the junction J2. Will cross the base region and will reach at junction J2, यानी जंक्शन J2 पे पहुंच जाएंगे इलेक्ट्रॉन्स, क्योंकि यहां से मूव किए और ये जंक्शन फॉरवर्ड बाइस है, ये जंक्शन आपका फॉरवर्ड बाइस है, और इस जंक्शन से मूव किए और इस जंक्शन को पार करते हुए, बिकॉज हमने वी हैव डिलिबरेटली मेक दिस बेस रीजन वेरी थिन एंड लाइटली डोप्ड. So this was the reason. This was the reason behind the base region. We want these injected electrons which are injected by this emitter, because emitter is injecting these electrons. The emitter is injecting these electrons here, and as soon as we are applying the polarity positive potential, we are applying the forward biasing basically. So these electrons are reaching at the junction J2. So this is the first scenario, and this scenario must be very clear, and this scenario is governed by these three facts which we have already discussed in the previous lecture, that these are the 3 points that which is related to the doping and the geometrical aspects of the transistor. So most of the electrons will cross the base region, like 98 to 99%, and will reach the junction J2. Okay, now we shall discuss the next scenario in this current flowing mechanism. What will happen at the junction J2? So first we need to understand for the junction J1. So we have and what is happening, this must be very clear to you. Okay, so this is just like a normal PN junction. We have discussed the basic theory of the normal PN junction. We just recall that theory, and now we are using that theory here. But here 3 points are extra. Emitter is heavily doped, base is lightly doped, base region is very thin. So if this region is very thin, then electrons will cross very quickly. Very quickly they will cross, and the less doped, so the recombination probability is very less. But there will be practically definitely there will be recombination, and this recombination will create this base current. So this is the base current because of recombination, and the electrons are moving here. Electrons are moving here, and we know that if electrons are moving in, then definitely there will be some current. So this current will which should be in this direction will be the emitter current. So emitter is injecting the electrons in the base region, and these most of those electrons will cross the base region and will reach the junction J2. And now we will see the scenario at the junction J2. And we have already discussed that we make this junction J2 reverse bias. For transistor as an amplifier, we make this junction J2 reverse bias. Okay, so here you can see lots of electrons. This is moderately doped. Now the junction J2 comes into the picture. तो पहले इतना समझना था हमें बस कि इलेक्ट्रॉन यहाँ पे आ गए. अब यहाँ जो जंक्शन J2 है ये रिवर्स बाइस्ड है. So this junction J2 is reverse biased. We have applied this is P type. So P type पे क्या लगेगा? Negative. So we have make this junction J2 as a junction J2 in the reverse bias. So now we know that with the basic theory of semiconductor physics or the basic theory of the PN junction, when we are applying the reverse biasing, then there will be some the depletion region will increase. So this depletion region will increase. So here this is the depletion region. Okay, so this is the depletion region here. So at the junction J2 already there was a larger depletion region. Now what we need to understand, we are injecting these electrons in the base region. So base is a P type. Base is a P type, or in the P type. In the P type region, the electrons are the minority carriers. So this phenomena is called the injection of minority carrier. So when we are injecting the electrons like this, so this is the injection of minority carriers. So here we are injecting, and what we need to understand here, what is happening here at junction J2. So junction J2 is ready with a very strong very strong electric field. The junction J2 is ready with a very strong electric field. Here you can see the electric field is very because this polarity will support the electric field inside the PN junction. Okay, and it will increase the potential barrier. We have already discussed in the reverse biasing. So now there is a very strong electric field, and what we need to understand, it will attract the electrons. This electric field will attract the electrons. We know that this electric field will repel these holes and these electrons, but this will attract all these electrons which are coming from here, because these electrons are in the base region and will reach the junction J2, and junction J2 is already ready with the very strong electric field to attract the electrons, and these electrons will move through the junction. These electrons will move through the junction, and this is how the current flows inside the transistor. So these electrons will reach here, and then the circuit will complete. I have drawn this like this. Actually, this must be like this. So that doesn't matter. So what you need to understand, the current flowing mechanism. The junction J2 is ready. The junction J2 is ready with the strong electric field to attract the electrons. These electrons which are being injected by the emitter. So emitter is injecting. So why emitter is called the emitter? Because it is emitting. If this is a N-type, the NPN transistor, then this is emitting the electrons, and this is a P-type. If this is a PNP transistor, then it will emit holes. So that's why it is called the emitter. And all these electrons are being collected at this terminal. That's why it is called the collector. It is collecting all those electrons which are coming from the emitter. So now what you can understand, this these all electrons are moving. These all electrons are moving, and they are reaching at this junction J2, and junction J2 with the strong electric field is attracting, because this electric field attract the minority carriers. यहाँ पे भी तो कुछ minority carrier होंगे पहले से. In this base region there will be some minority carriers, and in this region there will be some minority carriers like holes. तो वो भी attract, उनकी भी current होगी, but that current is very small. That is a leakage current. That current definitely will be here, and we will discuss those currents separately, sophisticatedly and precisely. Sorry, in a precise manner we will discuss all the currents. But right now the big picture is this, that this is how the current is flowing inside the transistor. So this is how the current is flowing inside the transistor. These electrons are being injected by the emitter when we are applying the forward biasing here, and then these electrons are crossing the base region, and very less electrons are recombining with the holes, and the 98 to 99% electrons are moving forward, and those electrons are being attracted by this strong electric field. Here we have created the reverse biasing. So this is how the current flows inside the transistor. So this is the current flowing mechanism inside the transistor. And what do you need to understand now, that when this transistor, now you can understand this is the current, and here this current is flowing, and here some all these electrons are reaching at the collector terminal. At the collector terminal, these all electrons are reaching, and so the collector current, there will be definitely a collector current in this direction. So there will be a collector current because electrons are going like that. And the name of the transistor is the transfer resistor. Now what was the requirement when we discuss the transfer resistor? If we flow the same amount of current from a low resistance region, if this is a very low resistance, R is very low as compared to this. If the same amount of current is flowing, if the, let us suppose the same amount of IR, then definitely this will be very high. So here we can get the voltage amplification. If this is a very small resistance like 1 ohm and 1 ampere current is flowing, then 1 volt will be there, and this is a resistance of 100 ohm and a 1 ampere current is flowing, the 100 volt will be the output. So this is the same phenomena we have obtained here. How? So this is the reason. This is the PN junction here where we have applied the forward biasing. The forward biasing we have applied here, and we know that in the forward biasing the resistance is very low, and we know that RD dynamic, even if we take the resistance, it is order of the 10 ohm or 20 ohm practical values. And this region where we have applied the reverse biasing, the resistance will be order of mega ohms or kilo ohms, because there will be no and we know that whenever we are applying the reverse bias in a PN junction, the resistance is very high, very small current, a leakage current flows. So we know that. So what essentially what we have achieved, we have applied a forward biasing here and a reverse biasing here. We have achieved this phenomena of transfer resistor. So basically the same amount of current which is flowing through a very low resistance is